Download this code from codegive.com, link in the description below. Debugging assertion failures in GHC with code examples. Assertion failures in GHC can be notoriously difficult to debug. They often stem from subtle bugs in the compiler itself, or from unexpected interactions between different GHC features. However, with a systematic approach and the right tools, you can usually pinpoint the root cause. This tutorial will walk you through the process, providing practical examples and explanations along the way. 1. Understanding assertions and why they fail. What is an assertion? An assertion is a boolean expression that is expected to be true at a specific point in the code. If the expression evaluates to false, the assertion fails, indicating a potential bug. In GHC, assertions are primarily used for internal consistency checks. They ensure that the compiler's internal data structures and algorithms are behaving as expected. Why do assertions fail in GHC? Assertion failures usually signal one of the following. Compiler bug. The most common culprit. GHC is a complex piece of software, and bugs can slip through testing. This is more likely if you're using a development version of GHC, example a head build. Unexpected input. Your Haskell code might be triggering a corner case in the compiler that was not properly handled. This is especially true when using advanced language extensions. Memory corruption. Less frequent but possible. Memory corruption can lead to unpredictable behavior, including assertion failures. Hessen bug. A bug that disappears or alters its behavior when one attempts to study it. Debugging tools can inadvertently change the program's state, making the issue harder to track down. Concurrency issues. If you're using concurrency, example I/O, parallel, race conditions or other concurrency-related problems can sometimes lead to unexpected assertion failures. What happens when an assertion fails? When an assertion fails in a compiled GHC program, the program typically aborts with an error message that includes the assertion expression, the Boolean condition that evaluated to false, the file and line number, the location in the GHC source code where the assertion failed, a stack trace, optional, a trace of function calls leading up to the failure, potentially very helpful, a descriptive message. Sometimes some assertions include a custom error message providing additional context. 2. Preparing for debugging. Recompile with debug symbols. The first step is to recompile your project with debug symbols. This will make the stack traces and variable inspection much more informative. Use the G flag. The debug and -profile flags for cabal and stack, respectively, achieve the same effect. If you're building the GHC compiler itself, you'll need to configure it with debugging enabled during the build process. See GHC's building documentation. Increase verbosity. Increase the verbosity of the compiler output. Flags like V or V3 can provide more information about the compilation process, which can be useful in identifying the point where the assertion failure occurs. Simplify the code. Try to create a minimal reproducible example, MRE, that triggers the assertion failure. This means reducing your code to the smallest possible amount needed to reproduce the error. This will isolate the issue and make it much easier to analyze. Try different GHC versions. The assertion failure might be a known bug that has been fixed in a later version of GHC. Trying different versions can help determine if this is the case. Look for related issues. Search the GHC bug tracker, example on GitLab, for similar assertion failures. Someone else may have already encountered and reported the same issue. 3. Debugging strategies. Here's a breakdown of several debugging techniques you can employ, along with examples. *A. Using rung C and dump simple, simplified core. This is a powerful technique for understanding what GHC is doing during compilation. Rung C executes your Haskell code by interpreting it through GHC's internal representations, allowing you to see the intermediate results of various compilation phases. Dump simple dumps the simplified core language representation, which can expose issues related to type inference or optimization. 1. Run with dump simple *. 2. Examine the output *. Look for the assertion failure in the dump.dumpsimple file. The output is in a pseudo-Haskell syntax called core. Focus on the code near the assertion. Try to understand how the sort function is being used and what types are involved. The core representation shows how GHC transformed your original Haskell code, which can reveal unexpected type coercions or specializations that might be causing the assertion. If the assertion fails in the core code, it strongly suggests a compiler bug. *B. The GHC debugger, XI, with breakpoints. For more complex debugging, the GHC debugger in XI is invaluable. You can set breakpoints in the GHC source code itself and inspect the state of the compiler as it executes. 1. Compile GHC with debug symbols *. If you have built GHC from source, make sure you've configured it with debugging enabled during the build process. This will make the GHC source code available for inspection in XI. 2. Load your project into XI*. 3. Find the assertion failure location *. The error message will give you the file and line number in the GHC source code where the assertion failed. For example, 4. Set a breakpoint *. Use the break command in XI to set a breakpoint at the line where the assertion failed. 5. Run the code *. Execute your Haskell code that triggers the assertion. XI will pause at the breakpoint. 6. Inspect variables *. Use the print command to inspect the values of variables at the breakpoint. 7. Step through the code *. Use step to step through the GHC code line by line, and continue to resume execution until the next breakpoint. 8. Analyze the state * by inspecting the variables and stepping through the code. You can gain a deeper understanding of why the assertion is failing. For example, you might discover that the type t is not what you expected, or that tv is an uninitialized type variable. *C. The trace function ***. The trace function from debug.trace is a powerful tool for injecting debugging information into your code without modifying it significantly. You can use it to print the values of variables at various points in your program, helping you track down where the assertion failure is occurring. Be careful as trace alters evaluation semantics and can mask or reveal bugs. 1. Import debug.trace *. Add the import debug.trace statement at the top of your Haskell file. 2. Insert trace statements *. Insert trace statements at strategic points in your code to print the values of variables. The trace function takes a string and a value as arguments, prints the string to str, and then returns the value. 3. Compile and run *. Recompile and run your code. The output from the trace statements will be printed to str. *D. Conditional compilation with CPP. C preprocessor, CPP, directives allow you to conditionally compile parts of your code based on compiler flags. This can be useful for enabling or disabling debugging code, or for trying different implementations to isolate the source of the assertion failure. 1. Define a CPP symbol *. Use the D flag to define a CPP symbol when compiling. 2. Use conditional compilation *. Use if-def, if and def, else, and end-if directives to conditionally compile different parts of your code based on the defined symbols. In the example above, the trace statement will only be included in the compiled code if the debug symbol is defined. *E. Bisecting the code ***. If you have a large code base, bisecting the code can help you narrow down the region of code that's causing the assertion failure. This involves systematically commenting out or removing sections of code until the assertion failure disappears. Then, you can add the code back in small chunks until you find the specific code that triggers the issue. 4. Code example, a more involved debugging scenario. Let's consider a more complex scenario that might lead to an assertion failure. This example involves type families and GADTs, generalized algebraic data types. This code defines a vec type, a type level list, and a type family append to concatenate the lengths of two vec_s. The bat append function is incorrect. When the first vector is not nil, but the remainder is nil, it will directly append the second vector without increasing the length. This can lead to type mismatches and, in some cases, assertion failures during compilation or runtime, depending on GHC's optimizations. Debugging steps ***. 1. Compile with debug symbols **GHCG assertion example.hs. 2. Run the code **. If it doesn't crash immediately, it means the assertion failure is triggered by optimizations or later stages. 3. Simplify the code **. Reduce v1 and v2 to the smallest possible vectors that still trigger the problem. In this case, simplifying them further than they are now may not be possible. 4. Dump simple **. This is crucial here. Examine the .dump simple file. You'll likely see GHC inserting coercions that fail. The fact that a coercion fails is a strong indicator that GHC is trying to force a value to be of a type that it isn't. Search for the call to bat append and trace its effect on the resulting types. The core issue is the incorrect type of the return value. It expects append XSYS, but the code doesn't always guarantee that. The type checker may be trying to unify append XSYS with some incorrect type derived from the wrong implementation. 5. Using trace **. This will show you the values of XS and YS during each recursive call, helping you understand the execution flow and when the incorrect concatenation is happening. You'll see the first element of v1, which is cons1 nil, being processed, and then when XS is nil, the second vector is directly appended without the necessary recursion. 6. Fix the code **. The correct implementation of append is. 5. General tips and best practices. Understand GHC internals, somewhat a basic understanding of GHC's compilation pipeline, parsing, type checking, core generation, optimization, code generation, can be helpful. Knowing which stage is likely causing the assertion failure can narrow your search. Isolate the problem. Focus on creating a minimal reproducible example, MRE. The smaller the code, the easier it is to debug. Read GHC source code. Don't be afraid to read the GHC source code, especially if you suspect a compiler bug. The code is well commented in many places. Use your IDE's Go to Definition feature to explore the functions and data structures involved in the assertion failure. Ask for help. If you're stuck, don't hesitate to ask for help on the Haskell mailing lists or online forums. Provide a clear description of the problem, the steps you've taken to debug it, and a minimal reproducible example. Report bugs. If you're confident that you've found a compiler bug, report it on the GHC bug tracker. Include a minimal reproducible example and a detailed description of the issue. Be patient. Debugging assertion failures in GHC can be a time-consuming process. Be patient and persistent, and you'll eventually find the root cause. Use the right tools. Choose the right debugging tools for the specific situation. Dump simple is often the most insightful, especially for type-related assertion failures. XI with breakpoints is essential for inspecting the compiler's state. Trace and CPP are useful for adding targeted debugging information. Remember he send bugs. Be aware that the very act of debugging, example adding trace statements, can sometimes mask or alter the bug. If you find that the assertion failure disappears when you try to debug it, try a different debugging approach. By following these steps and using the right tools, you can effectively debug assertion failures in GHC and contribute to making Haskell an even more robust language. Remember to focus on creating minimal reproducible examples and understanding the compiler's internal workings. Good luck.